I will present the identification of seafloor geomorphological features. So the third presentation early in the morning. Now I will show you a lot of videos, and I will also present what we are going to do or what we are hoping to do in Santorini, just to connect the seafloor topography with the virtual reality in a way. Okay, we would love to do that, but we are at the first steps. Okay, and then you are going to present your presentation as a group, and then we are going to have a coffee break, and then for 30 minutes I will try to present as much as I can how we process the SWOT data and what we are doing about the acquisition, SWOT acquisition, and seismic survey in general. Okay, so we will play. So I changed the order of the presentations. Okay, so but the most important thing is that we need to listen to your presentations. You need to present your own work, and that will be also the latest interview of you also, because tomorrow, because of the train strike, and the Italian student will not be here, and we also need to leave early to catch our flight. I think that we will finish the lessons on the coffee break. Malcolm will do his presentation, then we will finish. So now that you are going to present your work, there is a good chance in front of the camera, okay, to say something about this Erasmus Summer School and what you are thinking and how can we improve the next summer school for Santorini. So, okay, so tomorrow there will not be student feedback session. It will be today because we are going to have also your presentations, and we will inform you about tomorrow if there will be 2 presentations or not. Okay. Yes. Okay, so let's start, not to gain some time. I will talk for about, I have an exercise after this, so you will all participate. There are a lot of videos. Okay, so you will stop me and we can have discussion and then we will continue. It's not only a simple presentation. Okay, I don't know who is familiar with the seafloor characteristics. Who knows about the main features of the seafloor? Do you know everything about the oceans and what we are going to find if we have the chance to dive on the seafloor and investigate the area? Do you know some main characteristics? Yeah. Except of the girls, except of the girls and the oceanographers, okay. So, not Ben, no, not student, no. And not Fabi, okay? Okay, so if you remove the water, I will try to do this also, okay? And I have next video, I have a very short presentation as a video presentation. Okay, you will find exactly the same characteristic, the same features that you find on shore. Okay, on the seafloor we have valleys, plain valleys. We call them as abbeys. Okay, so they are plain valleys. We have also some mountains. Some of them, they are out of the sea surface and they are creating some small islands. Most of them are volcanoes. Okay, but the most characteristic feature is the mid-Atlantic ridge. Okay, so it's in between, in the mid-Atlantic Ocean. Okay, and all over the place, but we all say mid-Atlantic ridge, and we are meaning okay, mid-Atlantic Ocean. Okay, there is a trough, okay, and small mountains also inside. So the 2 tectonic plates are moving apart. Okay, here. You see, this is a feature. This is the mid-Atlantic ridge that is continuous also here, also here, also here. So these are the places that they are moving apart, and all the magma is coming from the very deep structure of the earth up to the sea surface. Okay, so this is the main characteristic of the seafloor. We also have very nice continental shelves. What we are meaning of continental shelf is the continuation of the land of the seafloor. So once upon a time, in the ancient times, this was not sea, it was land. So most of the cities and ports, the old one, the ancient one, you can find them on the continental shelf. And then we have slopes. And on the slopes, we have a lot of canyons. Okay, so a small video without talking, she will talk, is the next presentation. Okay, it's playing. Okay, come on. Double click. do that. How can I play the video? No, but control. Here. To the screen. To do what? Zoom out. Okay, and play. Yes. Okay. So.
Ocean floor features. When you imagine the ocean floor, what's it look like? You may be surprised to learn that the bottom of the ocean is a dynamic place with higher mountains and deeper valleys than any found on land. It is a mysterious place too. Some parts of the ocean never receive sunlight, and the pressure of the water is greater than several jumbo jets on top of your body. With such hostile conditions, how do scientists even know what the ocean floor is like? In some ways, gathering information about the ocean floor is similar to learning about space. Sometimes people can travel to the ocean floor in vessels specialized to protect them from the pressure and cold. Just like space, however, many missions are unmanned. Scientists can indirectly determine information about the ocean floor, just like how they use radio and infrared telescopes to observe the sky. One method of indirectly collecting data about the ocean floor involves using sound waves. By reflecting sound off the bottom of the ocean, scientists can map the topography or shape of the ocean floor. If sound waves are sent deeper into the ocean floor, scientists can even learn about its composition. Plate tectonics work to continuously change the topography of the ocean. Just like the plate movement below land masses, the changes may be slow, but they are responsible for the mountains and trenches that comprise the dramatic landscape deep under the water. Earthquakes may even happen underwater, resulting in a giant wave called a tsunami. Divergent boundaries are one example of how plates move in relation to one another. When two ocean plates move away from one another at a divergent plate boundary, magma rises up to create a ridge. The deep crack created in the center of the ridge is called a rift valley. A deep trench is formed where an oceanic plate moves under a continental plate at a subduction zone. At more than 10,800 meters, the Mariana Trench is about 2 kilometers deeper than the height of Mount Everest. Volcanoes also form at subduction zones. When the plate that is pushed downward melts, the magma may rise up to the surface. Volcanoes may also form away from plate boundaries at hotspots. Hotspots are locations where magma rises up through a crack in the crust and reaches the surface. Initially, this forms an underwater mountain called a seamount. The Hawaiian Islands are an example of a series of volcanoes that formed over a hotspot and became large enough to reach above the surface of the water. Some volcanoes may evolve into a geo over time. Geos are unique because of their flattened tops. These structures start as seamounts, but after their tops reach the surface of the ocean, they are eroded away. This erosion gives geos their characteristic appearance. So far, you have learned about some of the features that result from the actions of plate tectonics. But what about the regions of the ocean where not as much happens? Let's start by going for a swim. The portion of the continent that is underwater is called the continental shelf. When you wade out into the ocean, you are standing on the continental shelf. At the edge of the continental shelf, a sudden increase occurs in the depth. This marks the beginning of the continental slope. Once the rate of descent decreases again, the continental rise begins. Although the name might seem to imply it, the ocean does not become shallower here, but it does not become deeper as quickly either. Finally, at the end of the see a small portion of the ocean. It is a fascinating place with many mysteries still awaiting to be discovered.
So, that was the video of what are the characteristics. Okay, so just to summarize, I found also this very interesting slide. So we have the continental shelf. Okay, be careful because you are going to recognize this on the maps that they are coming. Okay, you will participate. Okay, so this is land, this is the continental shelf, this is a plain surface without a lot of slopes values. Okay, this is a slope. As you can see, you can find here a lot of landslides. Here you can find also canyons. Okay, this is abyss. This is the abyssal plain. This is the plain. Okay, like a valley. Okay, these are the seamounts. This is mid-Atlantic ridge. And just to say something from the geologist, this is the transform faults. Okay, these are the strike-slip faults that cut the mid-Atlantic ridge. Okay, and also these are the trenches due to the subduction of one of the tectonic plate to the other. So this is our trends, and then again slope, and also slope and continental shelf. Okay, so let's play again. If you want, what we are going to try to do also in virtual reality, we want to remove the water in order to find out all the geological features, the morphological features on the seafloor. So we are trying to do something like this. Okay, just to have a view, if we have glasses to go around to see the continental slope, okay, and also the ridge, the mid-Atlantic ridge, abyssal plain, mid-ocean ridge. Okay, this is Atlantic Ocean. Moving from one place to another, this is the mid-Atlantic ridge, this is Africa. But we have already removed the water. Okay, that's why you can see the sea top morphology. And you see that the mid-Atlantic ridge is all around the oceans, the India. This is the Mariana Trench, 11 kilometers, 2 kilometers more of the Mount Everest. And also in this plate, one is moving apart, and from this side, the tectonic plate is subducted from the ceiling. You see, this is the seafloor topography in a resolution of almost 1 kilometer in size. And of course, that was the location of Titanic. And the island is the only place on the earth that you can find Abio, okay, the mid-Atlantic ridge on land. Okay. So, onshore, offshore morphology. Okay, so let's move and come to Mediterranean Sea, okay, because this is a European project, this is Erasmus. Okay, so some years before, a lot of scientists from different institutes, they gave in a database in France, if I remember well, so they all there in that place, they gathered all the SWAP data in a not very high resolution, up to 500 meters, now it's better, it's 250, and they created this sea topo bathymetric map. As you can see, the blue colors indicate the deepest part, and the deepest part is here in Pylos, of the southwestern part of Pylos. 5,200 meters is the deepest part of the Mediterranean Sea. So you can see the valleys, okay, the plains. Yeah, it's not abyss. The depth is almost 5,200 meters. Also, you can see the trends here, and also the volcanoes here. This is the Italian. This is the Greek volcanoes. These are some seamounts. This is called as Eratosthenes seamount that was a part of Africa that was moved to the north. So these are a synthetic topographic map showing onland and offshore, okay, bathymetry and also topography. This is also what we are doing as a geologist. We are taking the topography and we are mapping the earthquakes and also the geology. We wanted to do that because we want to see where are the active parts in the Mediterranean Sea. And as you can understand, the active parts are in the places that you have subduction. Okay, at the southern part of Crete and also in Peloponnese, and of course in Italy and here in the Atlas mountain. Or we want to map all the canyons, because we are mapping. Why we are mapping canyons? Because we have a lot of landslides, and of course we have tsunamis and earthquakes and so on. So they map the whole area in the Atlantic Sea and they indicate all the landslides and the canyons. Okay. And some examples in order to move. Okay, so in the bathymetry you can see the seafloor topography very well. So you can draw the canyons and you will try to find the continuation of the canyons on shore. So this is not only a small river, okay, on the seafloor. Maybe this continues from the land and also goes to the seafloor. Okay, this is a part in California. What we are doing, we are having a shaded relief topography, putting only gray color, okay, and then we try to create some morphotectonic maps indicating all the morphological features. For example, these are the landslides on the seafloor. Okay, showing only some examples. In Greece, okay, except of the landslides and the canyons, we have also basins, like Corinth Gulf. Okay, in this Corinth Gulf, all these blue color indicate that this is a huge basin, and the deepest part is 820. Okay, so you can see, plain valley. Okay, but we have a lot of, we say, active fault zones. You found a lot of active fault zones that trigger tsunamis and earthquakes and so on. What are these? These are the abrupt slopes here, and you can identify these active fault zones if you see that all the isobats are very dense, and then you have an abrupt slope. This is very interesting also for us, because this is an active fault. Okay, it has exactly the same characteristics as the on-land active fault zones. Okay, and also you can see a lot of canyons here in this area. In a better way, here you can see these are canyons. You can see the canyons, the small valleys, okay, and a lot of landslides. Or if you map the area in a better multi-beam system, I will show you in my presentation, you have better resolution, and also you can find out the scarp of the landslide. These are huge scarps that are producing landslides. Okay, these are some main characteristics of the seafloor. And also, what we are doing at last, we merge the offshore data and the onshore data, okay, and we are find out, okay, these are the canyon, the submarine canyon, but the continuation is here on land. So you have a river, and the river continues, ignores the sea, and continues on the seafloor. This is very important for the geohazards. Okay, or what one of our students did is that, okay, he had on-land and offshore data. He created a model in GIS, okay? So we will have this model, and we'll put it on the virtual reality, and we can play and we can fly. We will be from the part of the seafloor of Corinth Gulf up to the top of the mountain, and we will see all the morphological features. For example, this is a very active fault zone here, just on the coastline, that created a lot of earthquakes and tsunamis. Also here, you can see that there are a lot of small canyons, and you can see there is no active part here. Okay, so you need to merge the data, and you need to see the topography in total, not only land or seafloor. And then you can also put geology on it, and you can play with that. These are the active fault zones that I told you. These are the canyons. These are the interpretation of the topography. So we need to do that in virtual reality. We need to play with these tools. But first, we need to understand what we are going to solve. So if the creative technology students, they cannot understand what we want to solve, it is not worth it. Okay, because as geologists, okay, we know, but they also need to know which are these main features that we need to emphasize for geohazards. Okay, and also, okay, this is the active fault zone. This is a 3D model, and of course, this is a view from on land. Okay, so what I found some. Yes, if I found the. No, here, no, yeah, yes. Okay, so in Japan. are doing some models, okay, not in virtual reality, but in 3D, just to show how they are creating a landslide on the seafloor. So I need to, how can I put them more fast? Fabio, do you know? Fast. Oh. I think Malcolm is making my life very difficult because he presented. Come on. Here. Yes. Here, you see? I don't want to show you all the video, that's why. Okay, so they created some models. This is in Japan, and they wanted to show how the landslide has been created and triggered the tsunami in 2011. So they are taking the SWAT data, they put it in a model, and they show the landslide. And they have the results. Okay, so they need to have very good quality SWAT data. Or, in the other video, yes. Okay, this is how the tsunami caused by landslides. So we need to be informed about the landslide, hopefully on the seafloor, because they can create a tsunami. Okay, some of you have studied tsunamis. Okay, you can show us how the tsunami has been created due to the landslides. So we need to model this. We need to put them on the virtual reality and show them around how the tsunami can be created. Like on this video, this is a 3D animation, okay, showing, okay, that a large mass of sand and mud can travel, move down to the slope, and then the water down, which may create tsunami waves. We have tsunami waves, okay, that they would travel very quickly across the ocean. It's very simple. So you can use this example also to educate people to understand of what we are talking about. So tsunamis can travel, and when they are very close to the land, we have the phenomenon of drawback. So the water draws back farther than normal, and then we have the inundation. So waves inundate the coast and destroy completely everything. Okay, these are some examples. I'm sure that you have found also some other examples in the internet. Okay, further back than normal and then back again. Okay. What's the? I don't want to see my presentation on the screen. That's why I'm facing some problems. Okay. Okay. So another. Tsunami. Okay, this is an active fault zone, okay, that has been activated. So the two parts are moving, okay, up and down, and the tsunami has been created. The waves are arising, okay. So you have the tsunami. If it was needed to wear glasses, you will see that you are very close to these sea waves, and you need to move and go back, okay. So we have exactly the same phenomenon. And of course the big waves now are coming and they will destroy the coastal zone suddenly. So these are geohazards that we need to show to the people in virtual reality in order to understand what we are talking about. So the big waves are coming. And of course, we have the distract results. You all know what was happening. And okay, some other features are volcanoes. We have landslides, tsunamis, huge active fault zones that they are activated. Okay, and also we have submarine volcanoes. Submarine volcanoes like the Kikemjeni volcano, which can show the seafloor topography. So you can see it's like a cone. It's like a normal volcano, on-land volcano, but if you map the area and if you have luck, and at that time the volcano is being erupted and you are using very good multi-beam systems, you can also map the bubbles that are coming out. So at that time, I think in 2017, yes, with James Cook, okay, the UK research vessel, okay, they mapped the area and they were very lucky because at that time the eruption was going on. Okay, so you can see the bubbles that are coming out. So this is a volcano, this is a cone, and also this is a caldera. Okay, it's a hole at the top. What else? So these are Mariana Trench, and they have mapped a lot of volcanoes around this area because all these volcanoes are very active and they erupted all the time, so they created a lot of tsunamis. And what I found is that they have already produced 3D visualization, and if you are wearing glasses, okay, you can have a look on this map and you can play around and you can see the morphology around these volcanoes. We will do that for Santorini. Okay, this is also the scopus of this Erasmus summer school. Okay, to see the morphology in the seafloor morphology in the virtual reality. And of course, as I told you, some institutes, they have already done this, okay, in Mariana Trench. And also, I have also told you about the active fault zone. This is very active fault zone, okay, in Skiros Basin. And much better, this is the well-known North Anatolian fault zone, the continuation of the North Anatolian fault in the Aegean Sea. Okay, so you can distinguish the active fault zone because you can see that here there are very dense isobats showing that you have very abrupt slopes. Okay, so this is the way that you can distinguish the active fault zone. These are the basins with a depth of almost 2,000 meters, 1,900. And also these are some small canyons. So around this is also a fault zone. This is a continental shelf. You can play the colors and play the seafloor topography. And again, so if you have SWOT data, come on. Where is it? I need my mouse. Here. Where's Malcolm? Yeah. So in the Google Earth, if you import the SWOT bathymetry, this is I think in Germany, Harvard port. If you import the SWOT bathymetry and also you have the Google Earth, you can play, okay, using this kind of material. Okay, you are wearing the glasses and you can search around, but also you have the chance to see, except of the features that you have seen on Tuesday, wearing the glasses, also the seafloor topography. Okay, this is the harbor of, this is port of Hamburg. Okay, so this is the deepest part. We are using blue color for the deepest part and yellow, orange, red colors for the lowest part, okay, for the shallow part. Okay, it's a good layer. So there's many examples. And also, this is a new application of the Google Earth. Google Earth Tour New Seafloor. Okay, that they want to show the seafloor topography. They are using almost 1 kilometer grid resolution about the seafloor. Okay, so they can show you the sea mounts.
And half of all of the ocean area that has ever been mapped. Let's begin our tour by visiting the Lamont Seamount.
Yeah, these are the sea mounts.
This chain of young seafloor volcanoes has summit craters and calderas, just like their counterparts on land. However, their slopes are pristine, unaffected by rain erosion.
And also you can choose another area.
Monterey Submarine Canyon and
The canyons that I told you.
Large subsea drainage system transporting sediment delivered by rivers and triggered by avalanches on steep underwater slopes with deeper abyss and high-speed sediment slurries called debris flows.
There are no houses, okay, or plants, okay. As you can see, the Google Earth on land.
The California State University in Monterey Bay
Yeah.
has collected new data on Cordell Bank off the west coast of California near Bodega Bay, an area whose fish and wildlife have rebounded since it was made a protected area 15 years ago. The southern base of the 10,000-foot high Mendocino Ridge
So this is the transport faults.
interior of the ocean's volcanic coast. This
see the active fault
That
zone.
was specific accretionary prism on the margins of the Oregon and Washington coasts. The seafloor of the Pacific Ocean is moving eastward and slides under the edge of North America. Here, the softer sediment cover above the much harder volcanic crust is being scraped off and squeezed into folds that produce the bands of ridges parallel to the coast. The Pittman Fracture Zone slices through the Pacific Antarctic Mid-Ocean Ridge. This ridge formed as Antarctica separated from New Zealand some 95
So this is an active spreading zone, okay, in New Zealand. So you can see there is a ridge, and then you can have a trend. Or in Hawaii and so on. Okay. And also, what else we can do is we can use satellites for mapping the seafloor. But the satellite, using satellites, you can. Is it playing? No. No. Yeah. Okay. So yeah, but using satellites, you can also map only the coastal zone. So you can have swath data, metric data, only coast to the coast up to the depth of 20 or 30 meters. Okay, so using satellites are very good because you need to map in detail the coastal line and also to have details of the ports, okay, or on the cities, very close to the cities. Yeah, you know this. And they have mapped a lot of the area around Cyprus. Okay, that's why I choose this video to show you what they have done. Okay, this is the Eratosthenes seamount. This is the continental shelf. This is the continental slope of Cyprus. These are a lot of mounds and a lot of landslides. Okay. Exactly. The sonars. I will give a presentation about the sonars. Next one. So they map the area on the port. Okay. 500 meters. And you have this result. So you have on land and offshore in detail. And of course high resolution because the depth is less than 20 meters close to the ports. Okay, and then what we would like to do for Santorini is what they have done as the divers. So what we are working on with Fabio and Mel is that these are an example for a diver. Why the virtual reality is very important to be used in order to explore the seafloor. So these are the divers. Okay, so they use virtual reality in order to find out all the structure that they wanted to be repaired. Okay.
To perform a full-scale virtual dive. VR Diver allows the users to rehearse on all types of operations
for
and
them.
emergencies
Okay.
that would not be possible in real-world
This is what we
conditions,
want to do for
such
Santorini.
as umbilical rupture.
We have already done the workflow.
Diving on track will basically using a simulator by being able to deliver more safe and more efficient solutions to their clients. With a simulator, you can reproduce previously happened.
We don't care about emergency situation in our case, but we want to explore the seafloor. Okay, and to see if there are some geohazards going on, for example, landslides.
I was quite surprised about how realistic the graphics were, and I was surprised to see how the physical interaction with the valves was working. It seemed almost like operating without in real life.
VR Diver
Just
is used in
imagine that you are on the seafloor of Santorini and you can walk and looking around, okay, and explore the ocean. And trying to find out the faults, the submarine volcanoes, to take some small rocks and put it on the other side. So use this example for the geology, for the seafloor topography. This is the VR of the seafloor.
Where they need to have a certain spatial orientation.
VR Diver reproduces the actual work site by loading real seabed scans and CAD models of subsea equipment. Single-user remote allows for performing training ranging from individual assignments to project team training.
Okay. And of course, this is an exercise, but before the exercise, I will show you what we are trying to do in Greece in cooperation with some other colleagues. If it's playing, it's not playing. I can see that in my screen, but you cannot see it. You can see it? No. Now? Okay. So we name that as virtual diver also. Okay, so if the project will be funded, it will be also be a part of Erasmus project, because also we will be in cooperation with some other companies. So what we are going to do, we name us virtual diver. Sorry about that, because this is the Greek title. Okay, so we have already done some work. So I will pass all the slides and to show you that example, you will be in Santorini and you will point out a place that you want to, and so it will show up in the utility that, okay, you are in this latitude and longitude. Then you can choose images, sounds, any text, and also the 3D view. And also you have some info about the volcanoes and the history of Santorini, and this is the Unity. And if the project will be funded, it will be great, because we are going to have import a lot of data. Okay, and what we are going to do is passing all these details. You don't need these details. You import data, and then, for example, okay, so you will explore the terrain data set of Santorini, moving around. Okay, they can open and select also the bathymetric map. We will give them the SWOT data. You can also you can also assign some points of interest. You will say, okay, I want to see this and this and this and this of interest from geology or from a tourist. But the most important thing is that we are scheduled, if we will be lucky, to do that. That you will stand at the highest point of Santorini, okay? You can have a look of what is going on around, and it can point out the geological formation of Santorini, or also point out where are the churches, the museums, the villages, and so on. And then you can dive, that's why we name us virtual diver. You can dive from there on the seafloor, okay? And you can explore the seafloor, point out some points, and you can also have some videos of the seafloor, because we have a lot of ROV data, for example, or they make a joke of me, of course. And also, you can have some small stories, for example, how this volcano has been created. Okay, so these are the plan. So what we are going to show you in Santorini, there will be some small project, okay, from this project. For example, the ML students, okay, they can create the volcanic history of Santorini. So they will try to take all the data and create the volcanic history, the different eruptions of Santorini showing up in the virtual reality. Okay, and also you can have a path, and you can have around, and you will be inside the seafloor, and you can look around, and you can recognize all the morphological features. Okay, and the different eruptions here around Nea Kameni, or the steep slopes. So, yeah, for example, you have a lot of information, or you are moving around, okay, or you have a lot of data and pictures of this place, or also about the fishes. And if you want to play and also to be participating in documentaries, you can easily give them the data. And for example, this is the history channel of what we did. So they fly. It has been shown in the history channel as Atlantis Found, the title. So you can see the seafloor topography of Santorini. These are the lava flows from different volcanic eruptions. This is the main capital of Santorini. This is Spira. You can see the basins. Okay, these are the basins, 390 meters. You can see the abrupt slopes. Okay, so you have an idea about the seafloor characteristics. Okay, so this is the plan. And so, just to add the lectures and to play with me, there are two exercises for you, not for the Greek students because this is from Greece, so it will not be fair. So you have 5 minutes to identify as a group these submarine features. You need to show me where you can find basins, canyons, fault zones, landslide, continental shelf, and volcanoes. And there will be another slide from somewhere in the world, so the Greek students can also participate. If they can, they will be here. They can show you very quickly because they know this place. This is Niseros. This is the volcano. This is Niseros. You saw Niseros in the Google Earth. You play around on Tuesday. Okay, so this is Niseros, and this is Kos, and this is Tilos. So you have 5 minutes to indicate, to work together, and show me. You will be here and show me some of these features. We have the Greek students to be here. Some of the Greek students, 2 of them, and some other students from the other country. And the Greek students, I'm not going to say anything, will correct, okay, the UK or French or Italian students. Okay, this is the deal. Okay, so 2 of you, 2 of your group, you may decide. I'm not going to pick up anyone. Okay, who is coming from the other countries? Okay, come on, Italian. Aha, Italy and Greece. I like that, for the volcanoes. Okay, that's good. Okay. Come from here, the one group will come here, okay, and the other group, okay, these are they can judge you, okay, so be careful, they can judge you, okay. So, you may start in any place. Yeah. Or maybe, I'm not going to talk. Don't tell them from the beginning, Fodora.
No.
Yeah.
So you said this is a canyon.
Yeah.
Okay. And also a fault zone.
You may decide, you can tell them their opinion, and then they can judge. Okay, tell them. Okay, what you are looking. You have basins, canyons, fault zones, landslides, continental shelf, and volcanoes. You need to indicate all of them.
Maybe this landslide. All of these and then the continental shelf. Yeah.
You said these are
Volcanoes.
And so when you will be ready, you can point out, for example, starting from the beginning, basins. And I will tell you if it's correct or not. So then the basins of this area. Okay. Tell them loudly if they are correct or not. Yes.
Canyons. These are canyons. These are big ones.
this, not this.
So active. Correct?
Yes.
So they bring avalanche.
Only to them, no.
Okay.
This is the continental shelf, okay. And this there, okay. And what about, did you find any volcanic debris avalanches? Landslides but created from the volcanoes, okay. This is a caldera. This is a huge caldera over there. It's a caldera. So it's correct. Debris avalanches, landslides from the volcanoes, where we can find them. This is a volcano, that's
Yeah,
correct.
these are volcanoes.
Yes.
Yeah. Show them, show them. Okay, this, can you see that, everybody? This is a huge volcanic debris avalanche, okay, at the southern part of Mysinos. So you can find, so this part here are huge blocks that came out from the volcano and downslope, okay? So, all of this. Okay.
These are not these blocks.
No, this is caldera.
Okay.
Okay, and also these are volcanoes. So ask me, did you find any difficulties to indicate the seafloor topography, the seafloor features?
Looking closer? No.
Yeah, no closer one. From the distance?
Yeah.
Okay, that's good. Okay, well done. Next. So, next. So, more difficult now. Okay, we are in the middle of nowhere. Somewhere. Okay? Oh la la. Yes. And you need to identify continental shelf, continental slope, spreading ridge, okay? Subduction zone with a deep trench, okay? Abyssal plain, a valley, okay? And some isolated seamounts. You have 5 minutes. Friends, students. Come. And also with Greek students, other students, and also the creative technology students from UK. And then Italian students can correct. Come on, Martin, come on. From here, the UK from here. Stay there. Okay, so you may discuss each other and then you can correct each other about the continental shelf and blah blah blah.
So we are in the between South America and Antarctica continental shelf.
Wow, that's good.
South
So-
America is there,
Yeah.
Antarctica is there. Some
That was my last question. Where is this place? That's okay.
Some of the
You found
islands
it.
are there. So continental shelf is the shallow part, so it's the wet part.
Okay, stop. You saw them continental shelf. Other thing. Don't tell them everything because you know.
So,
Yeah.
and continental slope is the yellow, and as we go into the green one.
Okay, you discuss each other and then I will tell you. Guys, again, so the other place. Really.
The continental slope. Spreading ridge is
Pardon.
sorry.
The Abyssal plain, the most deepest part, very plain. That's good. Okay, Martin, show us something. I know your name, unfortunately.
Yeah. Isolated seamounts.
Yeah.
Going on here.
Okay.
See them? But
Yeah.
probably that a lot.
Yeah. What else? Show me something different. Yeah, this is true. Yeah. What is this? What is this that you are showing? Where is the opening of the ocean? Where? Where you can find the two tectonic plates that they are moving apart? Where? In which place? In the map? Not you. You're not lucky. Very difficult question. This is very difficult. For the people that they are not geologists, this is a very difficult question. You may discuss each other. Okay.
The place where the
Yeah.
tectonic plates spread apart,
Yeah.
it's like a ridge, so maybe
Yeah.
it's shallow parts, and and you can see a symmetrical features
Okay.
between plates. So you may see both the same features on the left side and the right side of the plates.
Perfect. Where? Show me on the map. I didn't see that. Show me.
This plate,
You may tell. Is it correct?
no.
Yeah. Okay.
This is Antarctica.
This is Antarctica. Yeah, this is land. Okay, guys, this is land. The green one is land. At the beginning, he told you that we are at the southern part of America.
South Patagonia is here. And so between South America and Antarctica,
Antarctica.
you have a spreading ridge. So
Where?
It's here.
It's here.
And very transverse faults.
False. Okay. Can you identify this? Can you recognize this?
Are moving like this.
Yeah.
And the ridge is here.
Was it difficult for you? Yeah. This is what I want to know. This is what I want to know. I don't. No, I care about if the geologists can solve me, but I want to know that the people that they are not geologists and oceanographers can recognize the seafloor fractures. Okay, so this is the spreading center. Okay, because he said that this is the center that you have the tectonic plates that are moving apart. If you remember the video at the beginning of the presentation, okay, moving apart. So you can see also the same features on this side and on this side. And then you have these fault zones, huge fault zones that are cut the spreading center. So here is a rift, okay, very deep. And from here, if you have the submersible and you go down there, you will find black smokers. You know what's black smokers? There are some chimneys where they are degassing black smoke. Okay, so these are the places that the magma is coming up. Okay, from the top of the seafloor. Okay, so these are the spreading center. Also here, somewhere here, and also on this, yeah, there. Okay, and where are the trenches? Where are these? The deep trench. Where is the place that is the deepest part here, and there is a trench. What do we say about trench? We have one tectonic plate that subducts with the other tectonic plate. So you have a valley here, like this, very steep slopes. Where we can find it? Where? Definitely. Yes. Yes. Okay, here. This is also very difficult. So here is the deepest part, okay, and you have this plate that subducts, okay, above this plate. Okay, and also you can find a lot of sea mounds. These are sea mounds. These are peaks of the mountains. Most of them are volcanoes, active or inactive. Okay, and continental slope, can you show me here the continental slope and the continental shelf in this area? This is land, okay, this is land. Continental shelf and continental slope. Yeah, yeah. Where? Yes, correctly. Okay, it's correctly because this is very low depth, it's very shallow, and it's very plain without any morphological anomaly. So that could be land once upon a time. Okay, and then you have the difference of the color. And if we wanted to show that in the virtual reality, we will show that this is a slope that's coming down. Okay, and then you have this is the abyss. Okay, so we have this abyssal plain here, and also here. Okay, is it more difficult to recognize morphological features on the seafloor or on land? The same, yeah. If you are familiar with this kind of maps, okay, you can find them very easily. But you need to be familiar with the colors, with the isobaths. Okay, but it's the same topography. Okay, good. Yeah. What? Yes.
Another one.
Here, coming apart. Yeah, this is subduction. Yes. So in this place we have these plates that are moving apart, and also this place that subducts, coming down below this place. Yeah, it's a very active. That's why we have a lot of earthquakes. And these are all volcanoes. These are all volcanoes. Sea mounts that the peaks are above sea level. So this is volcanoes. Okay. the other question is, okay, this is the southern part of America. Okay, so you can see that from the eastern part, you have a continental shelf. Here, you tell that, and then the slope. But from the other part, from the western part, you don't have so much wide continental shelf. Okay, has been destroyed completely, and then you have directly a slope. This is more abrupt morphology, abrupt slopes. Okay, because from the geological point of view, this is the Pacific Ocean that is coming down. Okay, of this South American plane. Okay, so yeah, play with the colors. I like that. But you need to know that what I was talking with Mel is that you need to know the morphological features, otherwise you cannot create it with the eye. You need to know the features. And it's definitely more difficult.
Why on the left-hand side it is destroyed completely, as opposed to the right-hand side?
This one, because we have a subduction. When we have a subduction, everything has been destroyed, so you don't have continental shelf. It's impossible to have. This is active margin, this is passive margin, as we say, from the geological point of view. Okay. Okay. Congrats to all of you. Okay. Well done. You did everything, so I'm very satisfied. So, this time is for your presentation now, okay, as a group.
Well, hello, my name is University of Boston too. I'm from the School of Earth and Environmental Science and then School of Creative Technologies. I don't know if everybody wants to introduce themselves, but I'm Stoichel and I'll be reading the script for the presentation. And this is Martin.
Hello.
He's prepared a little AR experience for the Kitanjani volcano. And,
I'll wander around and let you guys have a look at it as they're doing the presentation.
Charlotte. Then Pat, Ebony, and Leah.
Okay.
Jamie is part of our team.
Okay, yes, of course. Not only photographer, yeah. Okay.
We're supposed to look at the brief overview of the submarine volcanoes. And the way they're formed is by features of the underwater surfaces where magma erupts and creates underwater volcanoes, I guess.
Yep.
And the majority of them are located near the tectonic plates. So when the two plates move, ridges form and creates eruptions. Normally, when you're below 2,000 meters under the sea, the pressure exceeds 280 atmospheres, which creates critical pressure of the water, so the water can't boil anymore and creates a supercritical fluid, which makes the volcanoes really difficult to detect. So, but some of them also exist in the more shallow parts of the ocean, which creates a lot of hazards and but sorry. And almost all of the volcanoes are not well mapped, so that's one of the other issues. So we need to identify and map all the underwater volcanoes. Example of that is the Colombo underwater volcano in the Aegean Sea, which was discovered in the 1650s, and its eruption. So the way it was discovered, the eruption managed to kill about 70 people and caused a lot of damages. The submarine volcano process, so the main characteristic of the eruption is as the volcano erupts, it creates, because of the water and the pressure, it creates the magma solidifies really quickly and creates volcanic gas, which will be really dangerous to the environment. And as it continuously erupts throughout the years, it could create islands by days, maybe thousands of years for that to happen. So we're going to look at the Kikamjani volcano a bit more in detail for the presentation. It's a volcano based in the Eastern Caribbean, and at the moment is one of the active volcanoes, so it's still active and can erupt. It's about 8 kilometers north of Grenada, and it's located in the southern Greenland. So this is the volcano's arc.
Yes,
Yeah.
that's the as you can saw before, and this is the location of Kikamjani, north of Canada. And here is the gravity model of the Kikamjani, and here is the current cone, and this is the under cone. And also you can see in this picture it has some landslide here on the slope and here, and this is landslide tail.
And the way this is produced is by the South American plate and the Caribbean plate. Subduction. And then when the plate is subducted, the heat melts and creates rising magma from the volcano, and that's going to create margins. And also
so you can see here on this slide the subducted plate creating the rising magma of the volcano. Both plates are actually moving in southwesterly direction, but this one is moving much faster. It's moving 20 millimeters faster, which is why it's causing the collision and the trench. And you can see the distinctive subduction zone here with the island arc, which effectively mirrors it there, creating the seamount and the active volcano. Okay.
The prime focus of the Kikamjani leg is to explore this fascinating submarine volcano called Kikamjani, which is located off the coast of Grenada. I think we're going to see some really exciting things. I mean, I can't think of anything more exciting than
It's one of my best friends.
And Kikamjani is the only submarine volcano in the Western Philippines. It's the most active volcano in the Western Philippines. And it erupts about every 10 years. I'm really excited about going back to Kikamjani because we were there in 2003. So it's been about 10 years since the last time we were there. So one of the objectives would be to go back and to explore that hydrothermal system to see if there are any changes that have taken place. If the volcano is going to become more active, then one of the signs of increased potential activity is that the hydrothermal system will start to ramp up. We'll see more gas, we'll see more fluids. So we can use the data that we collected in 2003 and compare that with the new data that we signed in 2013 to see if there are any changes that suggest that the volcano
This is from Greece, from the Marine Expedition 2010 and 2011. It shows us a lot of similarities because the two volcanoes have a lot of similarities. These are bacterial mats that cover the whole volcano.
So there's like a big
But this is
plate
Kikamjani.
taken out of the crater. And that's normal for submarine volcanoes that have these debris avalanche collapses. So during the growth of the volcano, one side of the volcano will actually fail, and it'll look like someone took a big bite out of the crater. And that's essentially what the current state of Kikamjani is right now. So we think that at some time in the geologic past, the ancestral Kikumjeni was a much bigger volcano, and it actually was above the surface of the sea. And at some point, that collapsed and went down into the sea basin called the Grenada Basin. Right now, the small Kikumjeni is essentially growing up inside this crater. And that's the way volcanoes evolve, is that they collapse, they rebuild, they collapse again. And as I mentioned before, these collapses are dangerous because they can produce tsunamis. So it's important to know the timing of these collapses in order to understand the risk of future events at Kikumjeni. One of the objectives is to bring a special device on the ROV to sample the gases in situ and to analyze those gases and to see what their composition is. So Kikumjeni, in that area of Grenada, there are very strong currents out in the islands off of Grenada. And the local fishermen, when they go out to fish, the boats are often buffeted by these strong currents. And so they feel like they're getting kicked. The Jenny part is the term for mule in the West Indies. So Kikumjeni means it's like being kicked by a mule. So the local fishermen who are around the area of Kikumjeni, the sea surface is disrupted and it's being turbulent and they're being kicked around. So the local fishermen say it's like being kicked by a mule. That's how Kikumjeni does.
Is that okay? No.
Here's the history of Kikumjeni. So it has about 14 eruptions in the past 70 years. So it's the first recorded data is from 1939, and the most recent eruption was in 2017, where it created.
Yeah. 2017, and it's just been recorded by the Seismic Research Center, and that caused them to pass information to the Grenada National Disaster Management Agency. And you can see this image here where they have the exclusion zone. That's been in place since 2017. It's just to not cause any hazards for boats. It's going through shipping routes, so I think they put that up.
So we have the eruption zone, and then this is the danger zone from any gases or maybe there's a tsunami. So they're prepared if anything happens.
So, as a newly discovered volcano, it's largely like unknown capabilities, and also because the eruptions happening mostly under the ocean, so we can't actually see them unless they break the surface. However, it's well known that volcanoes along such a plate margin can be explosive, with producing more silicious evolved magmas, which create more viscous magma, which is then blown apart as the gases expand. Analysis from the Kikumjeni volcano shows that we have basaltic and basaltic andesites, and suggests a mixture of primitive magmas and more evolved magmas, and effusive, which would give us more effusive eruptions, as well as more explosive eruptions. So they're mixed here, with then finding that also fragmented tephras and pyroclastic flow deposits, which suggests explosive eruptions also are taking place. And also the underwater nature of the volcano will also cause more explosivity. The magmas mix with the waters, and the heat is transferred then to the water, cooling the magma, causing it to be blown apart, and also for the water to very quickly vaporise. And so there's been a bathymetric studies, obviously, how we've got our data for the models. That's showing here in red, we can see cyclical, so it's 2003, 2013, 2013, 2016, and 2016-17. So we've got a cycle of growth and then collapse, and then here it's it's shallower, so it's shallow, and then it's obviously we've got collapses, and then further cone growth. So at the moment, the cycle is actually preventing there being a tsunami hazard from the landslides because it's keeping it shallow enough so there's not too much debris to cause a landslide. But if it was to grow up above the ocean, then we might have some concerns.
This video.
Yes, this is the Kimjani volcano.
Correct.
Eruption.
You can see here the degassing as well,
Yeah.
which also helps it to be more effusive and less explosive eruptions.
Yes. Okay, so you can pass this, of course. The dangerous, okay.
It's super dangerous. I mean, because there's short and explosive eruptions could be caused because the volcano is still quite active. And currently, the volcano is on yellow alert, so they have a monitoring system in place to constantly monitor the activity just in case. Also, the volcano causes a lot of hazards to ships, so when they sail by, because of the water pressure, it causes the ship to sink. Also, the debris starts to float.
And also like secondary geohazards which are caused by this. Maybe not specifically for Kimjani with the tsunami at the moment. With them monitoring the gas release and everything, I think they can see when this will become a problem. But right now I think these are the main problems for Kimjani, especially with the basaltic projections that matches the characteristics of this.
So do you believe that it's important to monitor submarine volcanoes or not? Of what you read in the internet, of what you know?
Yes.
Is that important?
Yes.
Do you know if any submarine volcano is being monitored?
We know what this one is.
This is not being monitored
Is it not?
regularly. No, they have
What is it?
marine expeditions every 6 months, I think, but they have not installed specific instruments on the seafloor. But there is, if you remember, on Manly Reservation, there is an axial seamount of the western part of the Northern America. Okay, axial seamount. I show you some ocean seafloor observatories. So there is a huge volcano caldera, that this volcano is being monitored, and also some volcanoes in the Japan Sea, very close to Japan. Okay, so we do not want to monitor the volcano, to put instruments there, and also Colombo. Okay, so did you find it that how the virtual reality can help the students or the tell me the agency, the civil protection agencies, okay, to understand about the geohazards of a submarine eruption? How the virtual reality? Tell us.
I guess one way could be if there's eruption and then showing the ship sinking, then you can just experience that or see it. See the dangers.
Yeah, believe it that I am the mayor of this island, okay? And you are some persons, some scientists. And then you need to persuade me that it's very important to give money to the scientists to monitor this Kimjani volcano. But what are you going to do? How do you persuade me?
I can show you they don't really see it, they hear it, but they want to see it as well. And I think it's better to show them before it's too late.
So, hi everyone. We are talking about paper wrote in 2004, and the paper is the morphology, setting, and processes of the Afen slide. Okay. So the localization of the area is 95 kilometers of northwest of Shetland Island. Shetland Island is in the north of Scotland. So the landslide identified in 1996 during an environmental survey for the Atlantic Frontiers Environment Networks. A series of transfer zones passed near the close of the study area. One of them is called the Victory Transfer Zone. So we see that there is a complex relationship between this slide and shear and structures. So what about the landslide characteristic? So the head of the landslide is at 830 meters below sea level. The lobe is 1,120 meters above below sea level. The length is about 12 kilometers, and the maximum width is 5 kilometers. And the geology of the site is mainly some deposits just beneath the surface of the lake.
Okay, so what kind of methodology you can use to study this kind of geohazard? So first of all, when we have a bathymetry, so the general altitude of the sea floor, we can use seismic methods to go deep in the landslide and to see on what is the different layers of the landslide and the componentry of the landslide. So yes, we can use seismic data to have a high spatial resolution data in 2D and 3D dimension, so in order to identify the different layers, and as well to characterize the entire morphology of the landslide. So we can see in this figure, like here it's quite small, but here is the landslide, the cross section here, and you can see the different layers of the landslide. And we can estimate also the thickness of the deposits here. So for example, in a more focused area of the landslide, so 3D seismic data, we can characterize some erosional features on the base of the landslide. So you can see the scale here. So yeah, in 1 kilometer we can distinguish some features. You have to know about this, but yeah, you can distinguish some things. And as well, debris flow here. So here's like debris, so a small lobe, not 2 kilometers wide, but yes, maybe 5 meters of height. So yes, we can identify some different features. Another methodology to characterize these kind of things is to do some sampling. So for this landslide, the researchers have about 20 samples available, and they use different sampling methods, alphabetic course, based on course, box course, and Devo course. So the limits of this methodology is that the shallow depth of penetration of this sampling is maximum at 6 meters, but the seismic data is a complementary method with this one. By sampling some samples, rock samples, outside and inside the landslide, we can both characterize the entire area and to distinguish some of the main features, the geologic features of the landslide. So it is a figure that shows the different characteristics of the surface deposits. And they perform as well some shear strength analysis, so geotechnical analysis with extensive tests, shear strength analysis, and moisture contents to know if there is some differences between undisturbed and disturbed material from the landslide.
Okay. So, based on the seismical data and the core that they gained in the scientific research, they try to reconstruct the different phases of the landslide, and based on the seismic data and on the morphology that we can see on the 2D and the 3D images, they could cover 4 different phases, which had a different transport method, and it made different lithology and different type of lobes in case of the landslide. So actually they tried to find out the age of the landslide as well, but because no analysis of the cores were made so far. I don't know since that time whether they made it or not, but they cannot correlate the exact age of the different stages of the phases of the side of the slide. But based on the morphology, they could make the following steps. So the first step was the biggest one, which is almost 4 kilometers long, and which created this huge lobe. So as far as they pointed out in the seismic study, the original scar would have been somewhere 900 meters below the sea level. And then in the second stage, another scar was created a bit higher, at around 850. So it made the slope a bit more stable. And then there was a further stage, first stage, which is not pretty sure, I mean, the characterization of it. So it's quite hard to see it in the 3D data, but based on the seismic data, they could somehow distinguish two phases, two separate lobes for stage 2 and stage 3. And there was a fourth phase, which is quite different compared to the first three one. Because in the first three one, I indicated here that probably the movement was kind of flow, so it was indicated by fluid manner in the layers that they could, as they could see it in the seismic data. But for the fourth phase, it was a bit different, so they could see some intact blocks in the seismic data, and this phenomena was related with a different type of movement, stick-slip type movement. So actually, it was not a real W slope like the others, indicated by the fluid manner, but it was a more slower, it was a more stable movement. And what was the reason for this whole landslide? They are not exactly sure about the triggering method, but the most likely should have been a seismogenic triggering method. If we just think about the first slide, when we saw the Victory fault zone, maybe a seismic event connected with that fault zone or fault should be the triggering method of the landslide, because otherwise the sediment is quite stable. So just on its own, it's not really likely to move, but maybe with this seismic movement, it was triggered to have 4 different phases for the movement. And it is quite a distant part of the Atlantic Ocean, so it doesn't face a real geohazard, like for example for heliogenic, where it might affect some areas close to inhabited areas. And it's not even affected, let's say, some petrol facilities or underwater cables. But it's an excellent study area to know more about the movement types of underwater offshore landslides. So it should be a good example to learn about the different phases and the different movement types of landslides that could be used later in areas that could affect some infrastructure as well. So thank you very much.
Did you find any destructive landslides close to the coastal zone that we have also fatalities in the internet? Did you search about this?
Yes.
Yeah, because
we find this.
Because Victor said that, okay, you choose that because it's a case study,
yes,
okay, for the landslides in order to recognize the types, okay, and the phases of the landslides. But do we know some landslides that they are really cause real geohazards?
They can cause tsunamis.
Yeah, of course.
But like risks.
Yeah.
Landslides linked with risk in submarine landslides, apart tsunamis.
For example, I saw you on Monday that there was a huge landslide before 9,000 years at the northern part of Scandinavian peninsula. Okay, so it goes a huge tsunami up to 12 meters, and we know that there were a lot of fatalities. So we do know that in 2004, the tsunami that has been triggered due to the earthquake, but also there were a lot of landslides, and also in Japan in 2011 there are some studies that they do believe that there was a tsunami was not only created due to the earthquakes, but also to the huge submarine landslides. So do you believe that the virtual reality can help to study these submarine landslides or not?
It depends on the place. So, for example, if we think about Norway, where the petroleum industry is quite rich, so there, for example, indicating different areas with a potential landslide or with a landslide that is already there, using virtual reality could be a great help for geologists as well, but maybe to show it to stakeholders as well, to take some safety measurements to protect the petroleum facilities.
And also to visualize the data. I mean, like this kind of cross sections. There is just one plane here, but with the virtual reality, we may just visualize the entire.
Good. Yes, of course. Of course. Or also, you can see what is happening at the ship surface. Okay, below that. Yeah, and you point out a very good thing that all the oil companies, when they are putting, when they are choosing the drilling site, like the Israel coast or in the Scandinavian, okay, definitely they have their technical methods to recognize the submarine landslides. They are doing slope stability models. Otherwise, they cannot put anything on the seafloor without searching for submarine landslides. Okay, this is very important. Okay, questions?
Well, the author that you have said that from our team is the earthquake, and more specifically the earthquake of the southern part of Lesbos Island last year. Some words about the geodynamic setting of the area of Greece. We are here, it's the subduction zone of the African plate under the European. So it is a very active area, and the area of the Aegean bounded by the Hellenic Arc and the North Anatolian Fault Zone to the north, and Lesbos, which is the area and the earthquake is here in the North Aegean part, the North Aegean Sea. And here we see all the distribution of the earthquakes. As we mentioned, we are in the subduction zone, where all the earthquakes occur. And here is the North Anatolian with a big amount of earthquakes. And here is Lesbos. You can see all the earthquakes. And so, about Lesbos, I would say it's in the northeast part of the Aegean Sea. It is part of an old volcanic arc center in the East Aegean that was active from 15 to 19 years ago. And its basement is composed of metamorphic rocks overlain by post-alpine formations.
So, the area of Lesbos characterized from three main fault systems. So we have the northeast fault system. So this is that one, and we have also the northwest and southeast faults that also continue in. We have them in the offshore, and this fault gives the earthquake. So about the earthquake, in 12 of June of last year, the magnitude was 6.3 Richter, and the depth was 13 kilometers.
the events of the June. The bigger star is the epicenter of the main shock, and the other one is the largest of the aftershock. And in the second map, we see all the epicenters after the earthquake of the 12th of June, and the scientists separate the area by the with the spatial reference. The black line is the force, and the B is the projection of the spatiometric projection that they use to separate the epicenters. Here about the focal mechanics of the earthquake. Then also the main shock and the aftershocks had the same direction. The earthquake was generated by the northwest southeast fault, normal fault, with a dipping of southwest. And this, together, we see the waveforms that they created, and we can observe that the mechanics are similar from the main shock and the aftershock. And here is from the story map that also Vera showed on Friday. Okay. We see the seismic sequence of the main earthquake on the 12th of June and after.
So impacts for the earthquake. The first reports induced by the 2017 Lesbos earthquake, apart from the fatality and 15 injuries, referred to numerous collapse and high-grade damage. Building damage were localized in western part of the affected area, and more specifically in the wider area of the traditional settlement of Brisa. Brisa is located further inland from the epicenter than other settlements, with less damage and seem like an earthquake impact paradox. Less damage was observed in other villas of the southern part of Lesbos, and minor damage was also reported from other localities of Chios Island, as well as from localities of western Turkey. First, considerations were presented based on the preliminary data released by the local earthquake rehabilitation organization. According to the first degree inspection conducted few days after the main shock, the buildings were characterized with respect to their main bearing system and material and immediate inhabitability. Here we see panel B and C summarize the absolute number and the rate of the habitable and uninhabitable masonry buildings for the most affected localities, respectively. As it can be observed, the largest damage throughout the island occurred in Brisa, where 436 buildings were heavily affected and around 18% has exhibited some degree of damage. Monumental construction, such as post-Byzantine churches, suffered some damage to their structural and non-structural elements.
Now for the management strategies, we have some internet sites that can show the earthquake at the time that it occurred. For example, we have the geodynamic site of Greece and from the National Capodistri University of Athens. And here is the story map that our research team created for the and now
research team went to Lisa directly after the earthquake. This is about the immediate management for the earthquake. Those are some damages in buildings. This is from photogrammetry. And drone surveys have been conducted in order to see from above the place and to create some orthomosaics. Those are the paths that the drone had done. And those are the pictures that were created for orthomosaic. The purpose was to create maps that show the damage in the buildings, and also our research team went there to see and to use collector for ArcGIS in order to see the density of the damages in Brisa settlement. This is the first orthomosaic, and the up image is for DSM. And the last result was that kind of map that shows the damage distribution for the buildings in Brisa settlements. And you can see that with the red color is the most damaged buildings.
Okay, questions. Why did you choose this specific presentation about the earthquake? So you presented some geohazards due to the earthquake that occurred on the seafloor. Okay, so why did you choose this example and you didn't choose something else? Why it is important for us, or as also geohazards, to show to the students?
We choose that first of all because it's in Greece, so we want to present something that happened in Greece because we are from Greece, and it's something that happened offshore, but we have damages on shore, and we can present the hazards of this event. This is for my.
I think that it's we show about the story map, but it's something that combines what we do here, the geohazards, the story maps, the management of an earthquake.
And even though it is offshore, as Lina said, that the impact is onshore as well. And the paradox is that the Brisa island, the Brisa settlement, was the main settlement that had the many damages. And we wanted to understand why in Brisa settlement were the main.
And one more thing is that because of the active faults, that we can compare the offshore and onshore faults that has the same direction too. And as Ms. Nomikou told us in last presentations, we have to see what happened and onshore and offshore too. So we have to compare this.
Okay, so the most important offshore geohazard is an earthquake, okay, because we have so many fatalities all around the world, okay, due to the huge earthquakes that occurred on the seafloor. Okay, so if I was a mayor of the city, if I was a mayor of Los Angeles, or in Hawaii, or anywhere else of the world, in which way the virtual reality will convince me that I need to be monitor all these active fault zones that they are on the seafloor and I cannot see them, and what about the consequences very close to the coastal cities, which are the tools that we will use from virtual reality. What can you do more of what the Greek colleagues did?
To increase the awareness of the people, because they don't know many things, what to do about the occurrence of an earthquake, because in Greece we have many injuries but one fatality. This is because it's not the main settlement in Lesbos. Many buildings were uninhabitable from the beginning, so there weren't people in the buildings at the time when the earthquake occurred. And I think probably
with VR, we can see at the time of the earthquake the buildings, the response to the earthquake, so to increase the awareness for the people. And also offshore we can explore the seafloor and see the active hot zone that produce the earthquake. How it looks like and how.
Like what they did in Japan, because for example in the Japan Institute, this is the seismological center of the Japan Institute, they do know about the huge earthquakes that occur every year or every moment. Okay, so they need virtual reality to explore the seafloor and to see the active fault zones and to be prepared of the tsunamis or the destructive earthquakes and so on. So we need to convince them using innovative technological tools. This is the one. Also, the Greek colleagues created these story maps just to show them about the damages. So it's important to have virtual reality of the seafloor, especially close to the coastal areas. Okay, questions? Yes?
Because in Italy we have the same problem.
Exactly.
So I was wondering if everything has already been rebuilt.
No.
And also, not yet. And if there's a plan about using the anti-seismic criteria.
Maybe, but because it's a very recent event, they haven't even have conclusions about what they're going to do to rebuild the settlement.
Because this is not something that scientists can do, it's of the municipality, the government, so they have to help. That we do from the scientific part is to dig when they're up there at the next day. So with a drone, they mapped all the area to have the results. But the next step is not from us. But I think with the virtual reality, if we have the opportunity to use it, also the government, the mayors, and people in general that they didn't live there to understand what happened, with the VR, they can feel and they can see what happened. So maybe the awareness will be, they will do something more to help the people.
Mine was a curiosity because we have in Italy there's a problem about ancient buildings, so they are trying to develop some shields for these ancient buildings and new buildings should have.
We have a seismic code. In the area, all Greece is split in different seismic areas. Okay, so we do know in areas like, example, Kefalonia, the Ionian Sea, or south of Crete, or close to the volcanoes, or close to the North Anatolian fault. Or this area, this is in areas that we have high seismic hazard. So the buildings must follow, okay, specific codes. If you want to build a house, you need to follow specific rules. Okay, that's for sure. Yeah, we have these codes also.
Yes, I think this is the main purpose of using the VR to use the information from scientists to other people to understand the hazards in any way. For example, in earthquakes, in volcanoes, to understand the simplest way of our scientific information.
Okay, other question? Yeah, sorry, Ben.
Why is there a large area of green houses that have not been damaged very much and a large area of red? Do you know if there was a difference?
They have a different structure. They are Matsuri or from Mars, they are different structure, different kind of buildings.
Geological formation. This is alluvial, this is alpine basement.
Okay.
So you can pick. So this
combination
is,
of both.
So this is exactly the boundary that we have two different geological formations, and the behavior of the geological formation is completely different. So this is a very good example how the geology plays a main role of the of the behavior of the earth, of the buildings during an earthquake. Yeah. So you can see the difference, the two parts.
Are the red houses also built on the area that would flood?
No,
if they're built on alluvium,
alluvium,
they're built on alluvial plain.
Yeah, yeah.
So if there was a rainstorm, it would also be the area that would
Up to now, we don't have this phenomena. But you never know. Yes. Okay.
And first of all, we have to define what is a tsunami. We can see that a tsunami is a series of waves in a water body caused by the displacement of a large volume of water. Generally, it happens in the ocean, but also it can happen in a large lake. In history, we have the maximum height reached by a tsunami that is of 520 meters, but this was a particular case in a little bay. Normally, in the ocean, tsunamis reach height from 10 to 40 meters. And we can see a tsunami. Okay. We have to define the difference from a normal wave and a tsunami wave. First of all, about the movement. In a wind-generated wave, we have that the movement takes place just in the uppermost layer, and we have that the motion diminishes with time. In a tsunami wave, the motion is in the entire water column down to the seafloor. We see other difference in wave speed, wave period, and wavelength. The main difference is that in a tsunami wave, the wavelength goes from 80 to 500 kilometers. And we see in this sketch that in the deep ocean, we can't detect a tsunami wave because the height is just about 1 meter. But when we go near the shore, we see that wave amplitude increases, and so we have a tsunami. We have three main generation mechanisms. The first one are the earthquakes. We see here an example which happened in Messina in 1908, but there are some other ideas that this was caused by a submarine landslide that is represented in this sketch. We can also have superficial landslides, such as in Stromboli. We have La Sciara del Fuoco, and we can have lots of tsunamis. The last generation mechanism is volcanic eruptions and collapses, and we see here that a debris avalanche can cause a tsunami.
Sumatra event in 2004 was generated by a huge earthquake. The earthquake occurred in the western coast of Sumatra Island, and at a depth around 30 kilometers, and it was offshore. The magnitude was around 9, and it was very destructive. So here we can see the geodynamical settings of the area. In this region, there's a subduction system, and at the boundary between the Euro-Asian plate and the Indo-Australian plate occurred this huge earthquake. We can see here the epicenter of 2004 event, and in this picture we can also see the movement of Indo-Australian plate, which moves around 45 millimeters per year under the Sunda and the Burma subplates, which are fragments of the Euro-Asian plate. Here we can see that this area is really active, and these are all the aftershocks. So there were plenty of aftershocks after the event in 2004, and there was particularly a huge event in 2005. Here we can see all the focal mechanisms and the epicenters. We talked about earthquake forecasting a few days ago. In this area, it's possible that in the future a large earthquake will occur in this region
because in the last event in this area occurred more than 200 years ago. So now the strain, now all the plates accumulated a lot of strain, so it's possible that a new big earthquake will occur.
Okay, so here from this map we can understand how big was the impact of the tsunami that was generated by this earthquake. This is a map that has been generated by NOAA, so the National Oceanographic and Atmospheric Administration, and we see different colors representing the travel times of the waves. So, for example, in this area in red, this means that all the waves that have been generated by the tsunami have reached this point between 1 hour and 5 hours after the main event. And so then if you move far away from the red, we have these yellow colors and green colors up to 10 hours after the event. And so we thought that this map was pretty interesting because it really shows how big the impact of the tsunami waves were, even kilometers and kilometers far from the main event. And now there's this video. And this video is like another remark of oh yeah, thank you. I can search it. I know how to search it.
So here. Okay. So we can now we can do.
It's not good.
And play. No. Is it right? No.
Com'è che fai a proiettare con questo? Non l'hai fatto? No. Con questo? No, mi stavo con questo tacco.
This is your presentation, so you need to check it on. Quick. Yeah. Okay, we can solve that in the YouTube. Yeah, okay, later. Okay.
Anche uscire alla presentazione.
Let's talk about damages. I decided to split in two part damages regarding in this part from economical damages and the second part about loss of life. The tsunami and earthquake the earthquake caused a mere total of 50 billions of US dollars, and compared to other natural events, is a low cost of money. And this because the tsunami affected traditional houses that are made mainly with simply wood, and there is not involved any particular structures or infractors of the impacted area. And what is very important to say is that the tsunami impacted with all the surrounding area, swept houses, cars, trucks, fishing boats, and all of these develop such a flow with a lot of debris, and all of that cause a very heavy damages and damages building and facilities. So tsunami is the two main occupation of Thailand, Sri Lanka, and that are fishing, destroying the boat and fishing gear, and tourism, simply destroying the villages, and tourists also deleted the reservation in the tourism villages. Also very important to say that water supply was contaminated by seawaters, and for a couple of years there wasn't water supply. So, and then let's talk about loss of life, because tsunami, in that event this event caused a mere cost of money, but a huge cost of loss of life, because we are talking about more than 200,000 loss of life, lots of injured, missing, and 5 million homeless, and is mainly by the tsunami, and we are talking about lots of people involved in this event. Relief agencies reported that 1/3 of the dead appeared to be children. That is very strong. And how much any life value? I put this because in risk management and for forecasting, we are used to talking about money. How much this building it costs, and we can imagine if it's worth to protect that building, but we are talking about a lot of people, and so that is the main focus of this presentation for me. And also India and Sri Lanka was hit by the tsunami, and they had about 3 or 5 hours to run away, but they hadn't I don't know, the efficient warning to reach a safe place.
So main problems were the high density coastal population, the lack of pre-warning, and the lack of knowledge of what a tsunami is, how it reveals itself, and how to deal with it. So how we can get ready for a tsunami? We think that countries must invest in education, people education and training, and in pre-warning analysis, like monitoring of each geological setting. Here there are some easy Red Cross tips, like make an evacuation plan, get to higher ground as far inland as possible, and most of all, be informed, because we think that education starts at school, and the Tilly Smith's story is a perfect example. Tilly Smith was a 10 years old English student from Sussex who learned about tsunami at school, and when she recognized the signs of water,
shoreline, and so he alerted her parents and other people on the beach. So the beach were evacuated, and there was no loss of lives. Easy tips saves lives.
One of the important consequences of the tsunami was the birth of the Indian Ocean Tsunami Information Center that gathered 28 countries that face the Indian Ocean, and it has the purpose to provide quicker information about tsunami and to disseminate more information about how tsunami happen, and when a tsunami happen, how to be prepared to what to do. They relies on a network of pre-existing seismograms and sensor of waves and sea level sensor. So there is nothing new about technology, but they want to gather information and to be able to communicate to every country quickly. Gregorio said that in Sri Lanka and India there was very more time to act and to escape, but they were not informed. They had no pre-warning. So they created a protocol on what to do. So there is a real-time data acquisition, very important. We discussed it already. And when an earthquake strikes, they have to decide quickly if the magnitude of the earthquake it has local, regional, or ocean-wide consequences. Local consequences are the most dangerous one because they have to go straight to evacuation. Regional, so they have more time to have something ready. So they disseminate the bulletin of the earthquake, and they decide also where there are the areas that will be struck from the tsunami. And the ocean-wide is very dangerous. What happened really, and they decided they alert all the participant countries, and they estimate quickly the arrival of the waves, so that we saw before the maps, and so they decide what to do. IOTC also states that their weak point, that is they are still unable to detect landslide and volcanic sources of tsunami. So we saw already what we can do, and also they are not able to provide enough pre-warning for local tsunami. So the suggestion is that they have to put new sensor capable to investigate different morphologies, and also they have to create a sensor network that is sparser for detecting regional tsunamis and denser for detecting local ones. Thank you.
Okay, thanks. And how the virtual reality can help the travel agency in Japan, for example, or here in Indonesia, to understand about tsunami and how they, for example, if I have a class, I am the municipality of a small village close to the Indonesian islands. Okay, why I may use the virtual reality? Why? Why do I need to create a classroom like this and put some cameras and have some glasses, and the people will come here and just realize what tsunami is? Is it helpful for the people?
Maybe for reconstructing wave propagation.
Yeah.
Different scale. Maybe from the ocean point of view, and then to a local scale.
Yeah.
As we saw, the indicator, the precursor are very easy to even a 10-year-old girl can recognize that. So it is important that few things very clear are learned by people. Young people also can help to save a lot of lives. So education is the main. So education with also control and monitoring.
So is VR helpful or not? Yes. So do you believe that if they have the chance to see the consequences of the tsunami waves that are coming towards them, Okay, so if you are in a class with a spangly, you can have a water, and you can feel the water flash in your face, so you can realize the power, okay, of the tsunami waves. And you need not, for example, not to protect your areas, okay, close to the coastal line. Okay, this is more important. Okay, questions? Yes, Ben.
One comment and one question. First of all, if you Google tsunami girl, since you mentioned a 10-year-old girl, there is a 10-year-old girl who figures as a character called Tsunami Girl, who is now an outreach program in Indonesia, and that's a cartoon, which is very good. The second thing is, you mentioned that you had about 30% of the victims were children. Why did you choose to show that?
Why? I didn't say.
Yes, what's the reason for saying that?
So the reason is because children are less strong than adult men. So when a wave impacts to a person, that if is an adult, he can resist all the force of the sea. A children do not.
Do you know what the percentage of children is in the Indonesian population?
I don't want to know.
I have it here, it's about 30%. So that means as many children were killed proportionally as other people, which I think shows the danger of using data without checking up other things. So what you're just saying there is as many children were killed as would normally be killed.
It could be also a marketing using of data, so you say that and it affects more people.
Yes.
If you say that a lot of baby.
That's where you have it. Relief agencies work on marketing as much as anybody else. So it's better for them if they can make it seem as more children were killed, and people feel sorry for the poor children, and they'll get more money.
Yeah.
But it's not necessarily true. So if you're dealing with the response or the protection, children might, for example, float better. So they might survive better. We don't know.
Yeah.
But you have to be careful with what you show.
Good point. Other question? Okay. Thank you so much for your presentation, for your time also. And if we wanted to have a small competition, which country do you believe that they present their data more accurately, more nicely? So we decided, no or yes? Yes?
It's
yes.
a difficult decision.
It's a difficult decision, but we are not going to decide. I'm not going to vote, also Ben is not going to vote. So take out a small piece of paper, write down Italy, Greece, UK, each of you, okay? Italy, Greece, UK, or France, and give it back to me in 5 minutes.